In this video, we're going to be taking a look at how to find the derivative of an inverse function. Before we look at the derivative, let's refresh our memory on what an inverse function is. So in order for a function to have an inverse, and generally when we talk about it having an inverse, we mean that is also a function. The original function f must be said to be 1-to-1. So what does 1-to-1 mean? 1-to-1 means that our function has only a unique output for every input, but also every output comes from only one input. So an example of a function that is not 1-to-1 would be something like y equals x squared. This is not a 1-to-1 function because an output of 4, right, when y is 4, this means that x could have been either 2 or -2. If I plug in an input of 2 or -2, I get an output of 4. So in order for a function to be 1-to-1, only one unique input can give me a single output. And similarly, it must be a function, so every input has to have one unique output as well. Now, if we're trying to find an inverse of our function, basically you take it out of function notation by letting y equal f of x, and then switching x and y, solving for y. If the function has an inverse, we denote it with this notation here. It looks like it's a -1 exponent, but it's not, because remember, -1 exponents means it's 1 over f, but this is the inverse function of f. So if the function has an inverse, then the graph of the inverse is just a reflection of our, and you can see that here. So we have y equals, the line y equals x there. Here's our function y equals f of x. The inverse is this function here. Now, if we're talking about continuity and differentiability of inverse functions, we first have to let our first function be defined on some interval I. And this interval could be really anything. It could be all real numbers, or it could be some other restricted interval. But if our function has some inverse on that restricted interval, or on that interval at all, then the following two things will be true. If our original function is continuous on its domain, then the inverse will be continuous on its domain. And if the original function f is differentiable on some interval containing the point c, and the derivative of our function at c is not 0, then the inverse will be differentiable at f of c. Because remember, when you talk about a function, right, a function, if it's defined at some point c, the output would be f of c. For the inverse, the input for the inverse would be f of c with an output of c. So the output that we get from f becomes the input in your inverse, and that's because we switched to the x and y here. So basically this is saying if our original function is differentiable at c and its derivative is not 0, then the inverse will be differentiable at f of c, at whatever the output of our original function is. There's no guarantee that the inverse would be differentiable at the original value of c, but it will be differentiable at the output. So how do we find the derivative of an inverse? So the graphs of inverse functions f and f prime have a reciprocal slope. Their slopes are reciprocals at these corresponding points. So if you have the point AB on f, then BA will be on f inverse, and the slope of the tangent line at this point is going to be the reciprocal of the slope of the tangent line at this point on the inverse function. And you can kind of see that demonstrated here, right? So here we have some curve f, and if we look at the tangent line to our curve kind of at this point here, you can see like it has we're told that its slope is 4, and then the inverse function here, its slope, the slope of its tangent line is going to be 1/4. It's going to be the reciprocal of that. And the corresponding points, right? So the point is 2, 3 here. So the corresponding point on the inverse would be 3, 2. You switch the x and the y. So the slope of our tangent at that point is 4, meaning the slope of the tangent on your inverse would be 1/4. It's reciprocal. And so we can apply that to these other problems where we're trying to actually find the inverse given some information about our original function. So in this case, we're told that our original function f is defined by 3x cubed minus x squared minus 8. We're told f of 2 equals 12. We might not always be told this. Sometimes they'll just say, here is f, and they'll give us f inverse, or they'll ask us to evaluate the derivative at some value in the inverse. And we would have to figure out what the input would be that would give us this in the original function. So the way that we would do that is we'd think to ourselves, okay, I'm trying to find the derivative at my function, my inverse function at 12. So if I'm considering the inverse, this is going to happen. So when the input is 12, I don't really know the output, but I know that this input here would be the output for f. So that output would be that there. So this value here is going to be the same as this value here because of the inverses. And since I'm given the value of my original, or I'm given the definition of my original function, I could set it equal to 12 and solve for x. But in this case, we're told that it's going to be at x equals 2. So that's okay there. So when f has the point 2, 12, the inverse will be the point 12, 2. And we know that the slope of our tangent line at the point 2, 12 will be the reciprocal of the slope of our tangent line at 12, 2. So what we need to do is find the derivative at 2 for f, and the derivative of f prime at 12 will be its reciprocal. So that's basically saying what we have here. It says if I want to find f inverse prime at 12, so the derivative of our inverse at 12, that's going to be equal to 1 over our original function, its derivative, at the output. And the output is just f inverse of 12. Now remember, this is just 2. It's the original input on our original function. So this is 1 over the derivative of our original function at 2. So let's go ahead and find the derivative of f and then plug in all that we need to do. So what is f prime of x? F prime of x is going to be equal to 3 times 3, that's 9, x squared, minus 2x to the first, and then plus or minus 0. So that's our derivative. What is the value of my derivative at 2? What is f prime of 2? 9 times 4, that's 36, minus 4 is 32. So that means the derivative of f at 2 is 32, which tells me the derivative of f prime at 12, right? Remember, the corresponding point would be there. So the derivative of f prime at 12 would be 1 over 32. This is the slope of my tangent line of my inverse at x equals 12, the corresponding point to my original function. Okay. So in the next examples, we're going to be taking a look at the derivatives using the inverse trig functions. And from time to time, you'll see the inverse trig functions written in one of two ways. We'll see the way that we're probably maybe more used to, this inverse sine of x. But if you ever see the word or this arc sine or arc cosine, arc tangent, this is just signifying the inverse sign. These mean the same thing. So if I ask you to find the derivative of arc secant, it's the same as asking you to find the derivative of the inverse secant function. So this you just have to recognize so that we can evaluate these derivatives. These derivatives are something that you need to just memorize. You could derive them, but the derivations of these are not the easiest, but we could do it. So you really do need to memorize these derivatives. They will come up and you will see them from time to time. So really it's important that you have these memorized. One thing that you might notice is the inverse sine and inverse cosine, their derivatives are basically identical. The only difference between them is this negative here. The same is true about the arctangent and arccotangent. Again, they are basically the same except for the negative sign. And the same is true with the arcsecant and arccosecant. Again, they're basically identical aside from the negative sign. And as you might notice, just like with our original trig functions when we're taking their derivatives, the derivatives happen on all of the co-functions. So cosecant, cotangent, cosine, cosecant, cotangent. So the co-functions, their derivatives come out negative. So let's take a look at trying to find derivatives using these inverse trig functions. So we're told that the original function y is the inverse sine of 8x squared, and we're asked to find its derivative. So what is the derivative of y with respect to x? Now, if we're thinking about the derivative here, the normal derivative, the derivative with respect to x of just the inverse sine or the arc sine of x, not with something inside it, is 1 over the square root of 1 minus x squared. Now, in this situation, we have something else in place of x, so we're just going to have to substitute that in place of x here. But because it's not going to be a simple x, we have to use the chain rule and multiply by the derivative of the inside. So we're going to do that here in this example. So it's going to be 1 over the square root of 1 minus, in place of x, we have 8x squared, so it's going to be 8x squared, that quantity squared, times, since this is not just a simple x, we have to multiply by its derivative. 2 times 8, that's 16, times x to the first power, so that would be that there. And then just go through and simplify, and we'll get that the derivative of y with respect to x is going to equal 16x all over the square root of 1 minus, so this 8 squared is 64, whoops, 64, and then x squared squared is going to be x to the fourth. And that would be that derivative there. Let's take a look at one more. In this one, we want to find the derivative of the arcsecant, or the inverse secant. So the derivative with respect to x of just the original arcsecant is going to be 1 over the absolute value of x times the square root of x squared minus 1. And in place of x, we're going to input anything that is in its place. And again, we'd have to use the chain rule if it's something other than just a simple x here. So let's go ahead and do the derivative of this one. We'll call it y prime. Y prime and dy dx, they're the same thing. So it's going to be 1 over the absolute value of, in place of x, we have 3x minus 4, times the square root of, I need to probably extend this a little bit. 3x minus 4, that quantity squared, minus 1. And then since what's in here is not just a simple x, we have to use the chain rule and multiply by its derivative. The derivative of 3x is 3. The derivative of 4 is 0. So it's going to be times that, which tells me that y prime is equal to 3 over the absolute value of 3x minus 4. You could expand this if you want, but there's not really any need. You can just keep it inside the radical as 3x minus 4 quantity squared, all minus 1.